Hello. So now that we've derived the heat equation from physical principles, we're gonna also now discuss two other key elements of any partial differential equation, which is initial conditions and boundary conditions. Basically, it's the idea that it's not enough information to solve a partial differential equation from the PDE itself, right? Just knowing how these variables change over time isn't enough. We also need to know how they start, the initial condition, and how they behave at the boundaries of this space region that we're looking at, the boundary conditions. And so we're going to discuss a little bit about what each of these look like. For the initial condition, uh, we can kind of just apply any. So first, the heat equation, just to review, is the partial u of partial t is equal to minus k partial squared u over partial x squared, right? And plus q if you're dealing with source charges, but let's assume we're not. So in this case, our initial condition is simply u at x comma 0 equals some f of x, right? And this could be anything. Now for the boundary condition, there's three main types of boundary conditions that are worth thinking about, right? Uh, the first one is called a prescribed temperature. This is simply when we say that, oh, u at, so if we're dealing with a rod as we are in this example, then we'd say, okay, u at 0, comma t equals some prescribed temperature of 2. And likewise, u at L, comma t is equal to some prescribed temperature of 4, right? Where this is x equals 0, and this is x equals L. Pretty simple. The next option is called is called insulated temperature. Um, this is basically when instead of describing the temperature at the boundaries, we describe the partial derivative of the temperature at the boundaries. So, for example, the most common time when this is used is when the boundaries are insulated, which in that case, partial u over partial t at both of the boundaries has to equal 0 because they can't change because they're insulators. And then finally, the last boundary worth thinking about is Newton's law of cooling, which kind of uses physics to kind of think about these boundaries. The idea being that there's probably a different material connected to the boundary that's a different temperature. And so we want to be able to assign these boundaries as a function of that change in temperature. And so Newton's law of cooling says the boundary at, say, 0, comma t should be proportional to, or then equal to some constant, call it h, times the difference between the temperature at 0, comma t and the outside temperature, which we'll call u outside. And you can write a similar function for the opposite boundary at L. And so these are kind of the three main boundary conditions that we can think about when we think about these partial differential equations. One way you can see these boundary conditions and initial conditions being applied is in finding the equilibrium solution to one of these problems. What that means is, okay, let's say we have we have a situation of a rod with an initial temperature, right, U of x comma 0, which is equal to, say, 4 degrees. And we also say we make both the boundaries insulated, so that partial U partial T of 0 comma T equals 0. And here, wait, I'll just copy paste this. And partial U over partial T of L comma T also equals 0, right? Then what we can do is we can actually figure out what the long-term solution, what the solution is for this equation after a very long time t, because we know that after a very long time, this equation approaches a steady state. And so partial U over partial T has to equal 0. And so if 0 is equal to minus K partial squared U over partial X squared, well then the solution to this equation is obvious. It's just C sub 1 X plus C sub 2 equals 0. And then we can solve, and now we can solve for these two variables using our initial conditions. So if we, sorry, not equals 0, equals U. And we can solve for C sub 1 and C sub 2 using our initial conditions as they're, using our conditions as they're supposed to be used. So if we plug in, well, if we take the derivative first, we'll get C sub 1 is equal to partial U over partial T. And we can say that initially, since at any at both 0 and L, the partial U over partial T is 0, C sub 1 then has to equal 0. And C sub 2 kind of is asking, what is the initial temperature, right? What is the initial temperature before the space component changes it? And so the initial temperature is 4. And so actually the solution to this partial differential equation in the steady state is U equals 4, which, if you think about it, actually makes a lot of sense, because if the ends of the rod are insulated and the temperature initially is 4, well, the rod is insulated, so the temperature can't change. The temperature U has to be a constant at 4. And so this is an example of how, this is a very simple example of how the initial conditions and boundary conditions are just as vital to solving the problem, to solving a PDE as the PDE itself, because you can see how these unknown constants come about, and there's no way to solve for these unknown constants unless we have our initial and boundary conditions.